Hello everyone. So we're going to talk about kinetic energy leaks. Kinetic energy is the energy of movement. Kinetic, right? So remember the first chapter is called kinematic, which is the study of motion. So kinetic energy has the same root of the word, meaning something in motion. So when an object is flying or traveling with any type of velocity, it will have energy associated with it. Again, which just means that it can do damage if it hits something. So the energy of motion. Now, so obviously, being the energy of motion, it depends on, two things. Motion and the object itself having mass, right? Now, but energy, of course, like any other kinetic energy, like any other energy that we learn, does not require direction. Now, actually, kinetic energy doesn't even have a negative sign. It doesn't make sense. It's either you have kinetic energy because you're moving, or you don't have kinetic energy because you're not moving. So unlike work done, we can still think of it as adding energy to a system or removing energy from a system. So it could be positive or negative, right? It's like your bank account, which can have money deposited or money withdrawn. But this is more like just how much is in your pocket right now. Kinetic energy is like how much money is in your pocket. Or when you ask someone, how much does like an item cost? Well, their answer could be $30, but you can never say negative $30, right? If someone asks you how much is like the book, you won't say negative $30 because it's either you pay me $30 or you don't. Like there's no negative in it. So it's a scalar quantity for kinetic energy, and regardless of the direction of the object, as long as you're moving, you have kinetic energy. And of course, it's also measured in joules, just like every single energy component that we have. Now, the energy, though, it depends on two things. The more massive an object is, the bigger the amount of energy that you have as your kinetic energy. So this is on your formula sheet. For kinetic energy, we're going to use EK, kinetic, right? K. Okay, so it depends on the mass of the object. More massive, more kinetic energy. That means the more damage it will do if it hits you. And then it also depends on the velocity of the object. Okay, the velocity of the object. So the faster the object is moving, the more kinetic energy it will have. The more damage it will do if it hits something. So for example, a very fast moving elephant has a lot of kinetic energy. A very slow moving mosquito has very little kinetic energy. But a very fast-moving bullet is an object that does not have a lot of mass but is moving extremely fast, will also have a lot of kinetic energy because it's fast enough. Now, it turns out though, however, that this equation has a special emphasis on the speed. So it depends, kinetic energy depends on your mass, but it's only a 1-to-1 ratio. It depends on the square of your speed. That means if you double the speed, you're going to get 4 times the energy. If you triple the speed, you're going to get triple square, which is 9 times the energy. If you quadruple the speed, 4 times the speed, 16 times the energy. 5 times the speed, 25 times the energy. However, for mass, if you double the mass, you get double energy. Triple the mass, you get triple energy. Quadruple the mass, you get quadruple the energy. So the speed affects it a lot more than the mass does. Now, just to complete this equation, there is a 1/2 in front. Unfortunately, the explanation of where this equation comes from requires advanced, not really advanced, but at least university level calculus. So we are not going to talk about that one today. Mass. So M is mass, which is obvious, I guess, kilogram. And V is your speed. You can say velocity, but since we are never going to mention angles or directions, I mean, what's the point, right? You don't need direction. It's either you have the energy or you don't. Okay, so it's technically a speed. All right. Okay, so now let's do a couple of calculations to warm up. A 60 kilogram student is running at uniform speed of 5.7 meters per second. So this is pretty respectable. And what is the kinetic energy of the student? So if you're running really fast, what is the kinetic energy that you carry? So 1/2 mv squared, right? So the equation is 1/2 mv squared. So it's 1/2 60 kilogram, 5.7 meter per second square. So don't forget the square. Using a calculator, if you can use it correctly, you get about 974.7 joules of energy. That means to bring yourself from rest to that speed, you need to exert at least 900, almost 1,000 joules of energy in order to bring you to that speed. Now, that's not about maintaining that speed. Maintaining, you have to continuously provide that energy. Okay? Next, what if you go to a movie? Now, have you heard of, do you know what a Rotten Tomato is? I'm always afraid that this joke will fall on deaf ears because people don't know what Rotten Tomato, if you don't know what it is a movie review website. So it's kind of saying that, if the movie is really bad, people get angry and throw stuff on the screen. I mean, people throw rotten eggs on things that they don't like in the past. So Rotten Tomato is just another thing that people will throw. So they use that as their idea, and I think so. Their website is called Rotten Tomato. So they rate movies based on how fresh the movie is. So it's either fresh tomato or rotten tomato. So if a movie get like a very bad review, then it will be it will be a Rotten Tomato movie. If the movie get really good review generally, then it's a fresh tomato movie. It's RottenTomato.com. You might have heard of it from the news from time to time. A movie will have something like a Rotten Tomato score. Anything below 50% is a fail. Above 50% is good. Okay, so let's say you're watching a movie and it makes you really angry because the movie makes no sense. You don't understand what's happening. Or the movie make you feel sick because the way they shoot the movie is very, shaky, and it makes you like nauseous. Actually, one of the movie did that to me. But it's like at least 20 years ago. It's a movie called The Blair Witch Project, I think. It's about like witch hunt, like about a couple of people who were lost on they were trying to find something, do like an exhibition in the forest. They were trying to look for this like tribe, and they got lost, and they get picked off one by one by this mysterious force or thing. Yeah, it's called Blair Witch Project. And I remember watching that movie in the movie theater. By the way, you have to be over 18, I think, to watch that movie. Not because it has any sexual scenes. It's because of the fact that it's a horror movie, right? And the whole movie is shot using a handheld camera. I'm not kidding. The whole movie is shot using a handheld camera, which has the quality of roughly like your cell phone from 5 years ago. Okay, so the entire movie is people running around being chased by this not invisible, they can't see it, by this thing, with like the whole footage is on handheld camera. So after like 2 hours of that movie, like the feeling that you have when you're getting like seasick or car sick? But usually you have to be in a car to get car sick, right? This is like you sit in a movie theater, you're not even moving, but the screen make you car sick. A lot of people actually get extremely nauseous at the end and throw up. I'm not kidding. I wasn't among one of them, but I have the urge to. I do feel like something is coming out of my mouth, like if I'm not holding it down. Seriously. Not a enjoyable movie. I mean, the whole premise was pretty fun like 15, 20 years ago, because they make it sound like this is actually like a lost footage that they found and they make it into a movie. Of course, it's just a movie, right? But yeah. So I would totally throw a Rotten Tomato at that movie screen if it was legal. But of course it's not, right? I mean, it's not a nice thing to do. So figuratively speaking, I will throw Rotten Tomato to it. So you're watching a movie and it makes you feel sick. So you have some tomatoes, you decide to throw it at the screen. All right. So let's say you throw the tomato, 2.1 kilogram. That's like a gigantic tomato, isn't it? I've never actually paid attention to that number until like today. That's like a huge tomato, like the size of your, like, fist, two fists. Like that's a huge tomato. Tomatoes are not supposed to be that big. It's not potato, right? Tomato is mostly liquid. So, yep, 1,000 joules. So how fast is the tomato moving? So kinetic energy. Now, so when you look at this, right? So they're just trying to make us go backward. 1/2 mv squared, but we are solving for v, which is how fast the object is moving. We are solving for v. We are solving for the speed, right? So a little bit of algebra is required in order to make this work. So if you solve this equation, you could just solve this equation for the v first. Multiply both sides by 2 to get rid of the 2, and divide by m. Okay, so it will be like 2 kinetic energy over m equals to like v squared. Something like this. And then you take a square root on both sides. So you get v is equal to square root of 2 times the kinetic energy over mass. So you do a square root at the very end, after the whole thing inside is done. Slowly substitute the numbers carefully. 1,000 joules of energy, and the mass of the gigantic tomatoes is 2.1 kilogram. 2.1 kilogram tomato, very big. So do that magic, and you have the speed of the tomato, 31 meters per second, which is over like 100 km per hour, faster than a car on a highway. You must really, really hate that movie in order to throw that hard, right? Maybe it's just really, really bad. All right, moving on. Okay, so now there is another way to find kinetic energy. A way, if you don't know the speed, if you don't know how fast the object is moving, there's another way to find kinetic energy of that too. Okay, so now we will start the argument by doing this. If there is a net force acting on an object, then the object must be accelerating, right? So if there's an unbalanced force, you must have acceleration, because F equals to ma. Now, but acceleration gives you change in speed, right? So if you're accelerating, that means you're going faster. You have change in speed. So, but this must be proportional to the change in energy. So change in your kinetic energy. Okay? So then we can conclude that, so if you want the change in your kinetic energy, that's equal to the amount of energy that you transfer to the object if you're trying to make it go faster. So that means this would equal to your work done. So if you're trying to push an object so that it goes faster, well, then the energy that you add to the object is increasing its speed instead of putting it. So there are two ways you can push an object. You can push an object horizontally, which makes it go faster. You can also pick up an object, which makes it go higher. So in the first scenario, if you're pushing horizontally, it will gain kinetic energy because it's moving faster horizontally. But if you push an object upward, that means picking it up, then usually it will just make it go higher. Therefore, you're increasing potential energy. So this equation is when you are pushing the object kind of sideways, so that you're increasing the kinetic energy. So, but what is work done? Work done is force times distance. Now, because the object is only increasing, the speed of the object depends on not only your applied force, it also depends on if there's friction or not, right? And in order to find kinetic energy, you need to know your speed, like final speed at the end. So you need to use your net force if you want to do this. Okay. Now, this version is not on the formula sheet. So like this particular version of the equation is not on the formula sheet. So if you want to add it on, that's your choice. So when will you do this? This is used if you are trying to find kinetic energy, but the question never gave you any speed. So you don't know how fast the object is moving at the end. Okay? So now, of course, you can find it, but then, that's one extra thing you have to do. So for example, so let's say someone is trying to run by exerting a force forward. Okay? And the net force, right? So that means, of course, you will have the forward force, but you also have like a backward friction. But everything included at the end, the net force is 260 Newton. Okay? And over a distance of 35 meters. So eventually you're here. All right? So what is your change in kinetic energy? So you're changing kinetic energy, so you can use that equation, which is net force times distance, 260 Newton times 35, which is 9,100 joules of added kinetic energy. Now, what does that mean? Does that mean your final energy, kinetic energy, is 9,100? No. It means whatever your initial energy is, the final kinetic energy is going to be 9,100 more. Okay, now, if you start at rest, your final kinetic energy will be this value. But if you start already have a little bit of speed, that means you already have kinetic energy, and then someone pushed you from the back with a 260 Newton force for 35 meter, then at the end, your total energy is 9,100 plus whatever you have to begin with. So like, for example, right, this is going to make no sense if you just look at the review. If you skip the video and just look at the answer key for the notes, this will make no sense. But now it makes sense. Now, so for example, your initial kinetic energy could be 500 joules. So what is your final kinetic energy? It will be 500 joules plus this change, which is 9,600 joules. Does that make sense? Like, the change is 9,100. So you were already running. Someone pushed you in the back, so you run faster. So that's the kinetic energy change, not the actual kinetic energy. We do have a question where you have to calculate V initial, V final. So this is a perfect one. A student pushes a 25 kilogram clay, which is initially at rest, with a force of 160 Newton over a distance of 15 meters. If there is friction, now it is friction, what is the final speed of the clay? Okay, so initially, the object is at rest, so that's V initial equal to 0. Then we're looking for V final, right? Okay, every speed is going to be able to give us a kinetic energy. So if your speed is 0, then kinetic energy initial is also 0. That goes without saying, right? Because it's 1/2 mv squared and you don't have a V right now. Of course, the final speed is not 0 because someone has been pushing it. So we will have to find out the final V. Draw a free body diagram because we need the net force to find change in change in kinetic energy. So normal force, gravity, apply force, and then friction. Okay, so we have these. Now, the only two is actually fighting is these two. The other one cancels out. Apply force is 160 according to the question. Apply force is 160 Newton. Not normal force. Friction is 75 Newton. So what is the net force equation in here? It must be FA minus FF. So the net force is 160 minus 75, which is 85 Newton. Okay, so that's our net force. Now we need that for the legs part. So now we can say, take the equation, change in kinetic energy equals to net force times the distance. We have the net force, and we have the distance, which is 15 meters. From these two, we can find the change in kinetic energy, which is 85 times 15, 1,275 joules. Now this is also your kinetic energy final. Right? Why? Why? Because your kinetic energy initial is 0. Okay, you know what? Let me just be very clean. Very clean about this. You're supposed to do change in energy equal to final minus initial. And then that equals to 1275. But then realizing that E initial is 0. So therefore, your final kinetic energy is 1275. Then I want speed though. So change your equation back to 1/2 mv squared. Now divide both sides by mass, multiply by 2, take a square root. The mass is 25 kilogram. And now you might want to try this in your calculator to make sure that you can do this. It's approximately 10 meters per second. Okay, so what you will need to do is times it by 2 on both sides, divide by 25 on both sides, square root at the end. Okay, so now this is done. At this moment, I want to talk about a movie character or comic character, the Quicksilver. He is a mutant from the comic X-Men. Now, according to the Wikipedia, he has a top speed, in one version of him at least, right, of 4,091 meters per second, which is a lot faster than even airplanes. So, what is his kinetic energy? How much energy, like, how fast, how much energy does he have to spend to actually get to this particular speed? You can pause the video now to have an idea. I know it's not exactly that speed, and it's faster because in the movie they want to do a more dramatic thing. But you can head over to, pause the video and head over to the course webpage to see the 2 Quicksilver videos. One is him running really fast, saving Magneto, Professor Xavier, and Wolverine from being shot at. He's fast enough that even bullet looks like it's slowed down in front of him. And it's a really cool scene from the movie. Another one is an explosion happening at a school. So the school exploding and Quicksilver tried to save everyone from the school. I just thought those 2 scenes were pretty fun. Okay. So now you're back, right? Well, those 2 scenes are fun, right? Cool. Now let's calculate the kinetic energy from Quicksilver. Now, before we do that, we need to know the mass of Quicksilver, and I looked it up on Wikipedia. He's a 73 kilogram person. So, to calculate his kinetic energy, we take the kinetic energy equation, 1/2 mv squared. Now, in our case, it will be 1/2 the mass of Quicksilver times his speed, 4,091, and square. So, okay, so I used my calculator, and I got an answer that is about 6.1 times 10 to the 6. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. 6.1 times 10 to the 8 joules. Now, how much is that? About 610 million joules of energy. Okay. So now let's say every time he has to get to up to that energy, his body need to spend, I mean, the energy comes from somewhere, right? It comes from his body. But where is the energy in his body coming from? From food. Well, then, how much food does he need to eat? So, of course, to measure how much food he needs to eat, we're going to use the only type of food that is known everywhere in the world. A Big Mac. You thought I was going to say like an egg or something, right? A Big Mac, of course. It's sold everywhere in the world. Now, I look it up from McDonald's website. Okay? One Big Mac has 2.3 million joules of energy. One Big Mac, okay? Has 2.3. I told everyone that the joules is a very small unit, right? Yeah. One Big Mac has 2.3 million joules of energy. Now, how do we find out? So what we need to do is take that number, 610 million, and divide by 2.3 million. And ladies and gentlemen, so the amount of energy Quicksilver need in terms of Big Mac equivalent is about 266 Big Mac. So that's why if you look at another superhero, The Flash, right? There's a TV show on it. He's always eating. He's always eating. And he's not eating healthy food either. He's always eating junk food like pizza and stuff, right? Chips, drinking, Coke, sodas, right? And that's why. In order to actually perform at that kind of metabolism, right? And that kind of speed, you need an insane amount of energy stored in your body. Okay, they're superheroes. I'm sure I'll give them the benefit of the doubt. I will say that they have like a very deep reservoir. They're well trained, right? They're super. But having a deep reservoir to hold a lot of energy doesn't mean it doesn't have to get replenished. You still have to eat consistently a lot of food, 266 Big Mac. I don't know, like every day, every hour, every second? I don't know. But you need to store all this energy in your body in order to actually use it at the end. And yeah, that's why sometimes like comic heroes physics or movie physics are a little bit, once you actually sit down and do the calculation, then you realize how ridiculous some of these things are, right? Because like for every time that he uses his power, he has to eat like 200-ish Big Mac. And I mean, I guess he's Quicksilver, he can eat really fast. But McDonald's still have to make that 260 Big Mac. That would take like an hour to make, doesn't it? So that means like before he can order another round of those Big Macs, he cannot use his power anymore. But in the movie, obviously, that's not the case. They just show you, for example, Quicksilver or the Flash from the DC universe just eating junk foods every day. Of course, they have to eat junk foods every day because they have to get the empty calories. If they start eating healthy and have like expensive food, they will go broke very easily. If they only want a calorie, the cheapest calorie is fast food. But of course, don't eat too much fast food. It's not healthy. If you can avoid it, actually avoid it completely. Okay, now another movie analysis that we want to do. This one you also have to look at the video on the course webpage, and this time look at the one about Spider-Man and Gwen Stacy. Okay, so now before you go, so the scene in the movie, which is also in the comic, I have the comic book. If you print out, I think it's in black and white, so you can look at the online version, which is in color. In the comic or in the movie it's slightly different. In the comic, she was pushed. Spider-Man's love interest, Gwen Stacy, was pushed from the top of the George Washington Bridge by the evil Green Goblin. So, what is Gwen's kinetic energy just before hitting the water? If the bridge is 184 meters below tall, and her mass is 55 kilogram. Now you can watch the movie. You can watch the scene on the YouTube clip right now, okay? And then come back here. Okay, now you're done, right? You watch a clip. You can see that she was falling, getting faster and faster, and at the very last second, Spider-Man caught her. So what is her kinetic energy just before hitting the ground? Okay, so here is our lady, Gwen Stacy. Her initial velocity is 0. All right. So what is her kinetic energy? Now, so what we need to do in here is, so one of the way to do this is by finding out her final speed, then we can get her final kinetic energy, right? So let's see how to do that. So this is her initial. So what is her final just before Spider-Man was able to catch her? Now, of course, this is a kinematics problem. We have the acceleration from gravity, negative 9.8. We have the falling of her, which is about the height of the bridge, which is negative 184 meters. We do care about the negative now because we are doing kinematics. Okay, so that should be enough. we have everything we need. V final, V initial, 2AD. All right. Now, so going through this, super easy. V final is what we need to find. V initial is 0, so this term is gone. And the 2AD. So 2 times the acceleration times the height of the falling object. So she fell 184 meters, right? So take a square root at the end, and you get the V final. Now let me do it in my calculator. Her final speed just before hitting the ground is negative 60 meter per second. Okay, so negative 60 meter per second. So that's her speed right before Spider-Man catches her. So let's turn that into kinetic energy. Now we can actually use the kinetic energy equation. 1/2 mv squared. So we'll put the velocity right here and put her mass, which is 50 kilogram, right here. All right. So now the kinetic energy just before. So she's carrying almost 10,000 joules of energy with her as she falls down. Okay. Now, unfortunately, the character, Gwen Stacy, died in the fall. But I would like you to actually think about something, though. Did she die because she fall? Does falling kill a person if there is no ground to hit? You might die of a heart attack because you're scared, but falling itself doesn't do harm. It's hitting something that does the damage, right? So Green Goblin pushed her off the clock tower in the movie, or the bridge in the comic. Spider-Man caught her just before she hit the ground. In the comic, I want you to zoom close to here. Do you see her leg area and the word slap on it? She was moving so fast and carrying so much kinetic energy that when Spider-Man catches her ankle with a web, she was stopping too suddenly. Now remember Newton's first law. An object at rest stay at rest. So an object in motion stay in motion. So her body, her leg, is now stationary because Spider-Man caught it. What about her head? A head in motion continues what? In motion. So Spider-Man caught her ankle, but the rest of her body, the most important part of her body, I guess, for a human being is our head. You can live without an arm, a leg. You can even live with only like half of a kidney. But you cannot live with half of the head, right? So she died partially because Spider-Man was trying to save her. Think about it. Spider-Man caught her at her ankle because that was the only area that the web can get it to, right? But by doing so, her body stopped too suddenly, and the kinetic energy was not going anywhere. Like the head will continue to travel at the same speed because a head in motion stay in motion. So what happened? Her leg area slaps. So technically, Green Goblin pushed her off the bridge. Spider-Man killed her by saving her. Now, you can go back and watch the video clip. You can see, maybe pause just before she hit the ground. You can see that after the web catches her in her ankle, her head still hit the ground like boom, and then she died. Right? So you cannot just stop someone by grabbing onto one of their body part, because that body part, yeah, it stopped. The other body parts are not. Okay, they're moving fast enough with such incredible kinetic energy that it cannot just be stopped like that. So, I mean, what is the only way to save her is maybe like if you have like Superman's power is to fly, legs to her, matching her speed, and put your arm around her head and her waist area, like the important area, so that her spinal cord are well protected, and just try to slow her down by applying like a force pointing upward, but not too sudden. Okay, not too sudden. If you apply a very sudden force, then the rest of your body doesn't respond to it as well. Then the rest of your body, for example, your head, will continue to go in the same direction. Just like what happened when your car hits an obstacle, your body fly out of the window, right? Because your body in motion continues in motion, although the car stopped. So in this really sad story, Gwen Stacy, Tony Parker's girlfriend, I think at that time, was technically murdered by Tony Parker. How about that, right? This was actually pointed out by a lot of physicists after the comic was published. Because physics people like to read comics. Yeah, science people like to read comics, actually. So a lot of people saw this and then go like, wait a second, then let's do some calculation. Yes, that's what Mr. Chang do. Like, you watch movie, I watch movie. You watch a movie, eat popcorn. I watch movie, do calculations. We both laugh I guess at the end, so it's a fair game. You know, to each of its own enjoyment, right? So now we will end here. End this here today. I mean, to Tony Parker's defense, I don't think there is a proper way to save her with like Spider-Man's power. I think the only thing would be to make a very huge web, like the policeman. You know, when they save someone who's jumping off a building because the building is on fire, so they have to jump off the building, a window to survive. So what does the firefighter do? Is they set up like a gigantic air mattress, like a landing, very puffy, like trampoline, like air mattress, and they have the person jump down to that, and that will slow down the descent of the person. But what is good about that is it will slow down because it's such a big area, right? It will slow down every part of the body at the same time, which is the proper way to save someone. You can't just grab a hand. Like, for example, someone's falling off a building, you grab their hand. There is a possibility that you will only save their hand. I know that sounds disturbing when you think about it. Like, imagine someone falling off a building and you live on like the first floor or the second floor, or you try to save that person by grabbing onto their hand. There is a possibility, however very unlikely to happen, if you don't get hurt first, right? That you will be able to save that person's hand, but only the hand, not the rest of the body. Okay, the hand just tear off. Usually it won't happen like that. That's like a very drastic, case. All right, because I don't think the person who's trying to save the other person's arm will be okay in that situation too. But we're talking about superhero saving someone, right? So of course we can assume that the superhero has better, stronger muscle, indestructible body, sometimes even in Superman's case. So the proper way to save someone is by providing a acceleration in the opposite direction of that person's falling motion, but apply it uniformly throughout her or his body, instead of grabbing like one part and letting the other part just continue to go. All right, so I hope I didn't just ruin that movie for you, or Spider-Man. Okay, so remember, that's it for today. 2 very short lessons. Okay,